part E, page 3. All right, so right now, we need to solve linear first order ODEs by formulas. Last time we developed that formula, okay? So we have that special form. Yeah, so last time, our general form of first order linear ODE, y prime plus p of x. Okay? There is a general function p of x times y equals r of x. Okay? So two functions in those two positions are general functions. Yeah. Here I want to use a concrete example to go through the whole method. Yeah. So pretty straightforward. Yeah. So this one, for the solution, let's recall the formula we need to use. All right. This is non-homogeneous because our function is non-zero. So non-homogeneous first order linear ODE. Yeah. And we need to find a integrating factor, right? Yeah. So from the p function, yeah, our function here is on our formula. Yeah, the final form of this formula, but this h, little h function, we take integral on p, then e to that negative h. Yeah. So here, e to the h. Yeah. So we multiply both sides. So finally we get this formula. Yeah. All right. Now, in calculation, yeah, we calculate h first, then we just apply this formula. Yeah. So, but in the calculation, there are some little places we need to be careful. Yeah. All right. First, h function, yeah, integral, yeah. So not too hard. Yeah. But here, when you do the integral here, there is an absolute value. Yeah. So in this example, I want to mainly explain how to handle this absolute value. Yeah. Yeah. Because other things are not hard. But we need to pay attention to this absolute value. Yeah. When we can remove absolute value, when we cannot. Yeah. All right. And negative natural log absolute value of cosine x. Negative, we can, put it inside. So that's the reciprocal of cosine, then secant. Okay? So this h function has two different forms. First, second, okay? Sometimes the first form is better, sometimes second form is better. Yeah. Depends. Why? Because when you look at this formula, some places the exponent you need to use negative h. When you use negative h, the negative natural log of absolute value of cosine is better. Because negative, then negative sign is gone, right? Some places you need to use positive h. When you use positive h, then this formula is better, this form. Okay? Yeah? Because you can do the simplification quickly, right? Yeah? So you use this formula, e natural log cancel out. Yeah. So you can get a simplified form faster. Yeah. So we keep both forms. Right. Now we work on this our solution formula. Yeah. Why? Solution. Yeah, but we need to simplify it. All right. So let's plug in. Yeah. The first we use this, negative version. Negative sign is gone. Okay. Second, because no negative sign, so we use this secant form, yeah, and so on. Okay, all right. Then E natural log cancel out, right? Yeah. So we have this absolute value of cosine function. Yeah. So here cancel out, but we need to keep this absolute value function form. All right. So then certain function, yeah. So certain constant, yeah. All right, yeah. Then we need to do some discussion on this absolute value sign. Yeah. Yeah. We cannot remove directly. Yeah. Yeah. So here the situation could be complicated. So we should be very careful. All right. So we need to consider two different cases. Yeah. The first case, under the condition cosine of x, this function is non-negative, then absolute value is gone, right? Yeah. The second form, where the cosine of x is negative, then we have the second form, okay? Yeah? All right. Yeah. Yeah, but here, actually, things not as simple as what you see here. Okay? Yeah, so let's look at these two conditions. Yeah. If you do not dig it very deep, you may not see any problem. Okay? Yeah. But if you dig into, you know, some deep level, okay? Some deep level, then you need to be very careful in this place. In this place. Yeah. The other two places outside integral operation, no problem, okay? But inside this integral operation, you need to be careful. Yeah. Yeah. Yeah, because the situation could be complex at this place. Yeah. Because when you say cosine of x non-negative, negative, can you describe it with more information? Because the question, what I mean is, these two conditions, do you mean for one point x? Yeah, because x, you treat it as one point. Another understanding, do you mean on one interval? Yeah, because sometimes you may consider this condition hold on some interval. Okay? On some interval. Okay? Yeah. So on the whole interval, it is true. Not just one point. The whole interval is true. Okay? So these two different ways of understanding. Two different ways of understanding. Okay? All right. Yeah. The simpler case. Yeah. The simpler case. For the interval case, yeah, this interval case. Yeah. This interval case, then it's correct. Okay. Yeah. On the whole interval, positive, negative, yeah. Then, you know, it's correct. Yeah. If it's not an interval, we may have some difficulty. Okay? If it's a non-interval case. Yeah. Because if you do not have the situation like this, then there is a possibility when you take this integral sine of 2x, absolute value secant of x, then you have the possibility, because when you take interval, it must be on some certain interval, right? Yeah. So, yeah, on certain interval. Okay. Yeah. Let me use this. Oh, sorry. Let me. Oh, why I cannot write? Yeah. Okay. Yeah. On certain interval, let me write this way: alpha and beta. Okay. Yeah. Yeah. Because when you do interval in the real-world application problem, you need to specify, you take your integral on what specific interval, okay? Yeah? Yeah. So otherwise, too much uncertainty, okay? Too much uncertainty, all right. But when you choose some arbitrary interval here, there is a possibility. In part of this alpha beta interval, cosine of x is positive. Part of the interval, cosine of x is negative. Mixed, the sign in this interval. So sometimes positive, sometimes negative. Then you cannot move this absolute value. Okay? Then you cannot move this absolute value. Then you cannot write these two forms. Yep, because you need to, inside your interval, you need to divide into two parts. Okay? The part of the interval of alpha beta, that cosine of x non-negative. Yeah, so you remove absolute value, use the plus sign. Then the complementary part, the remaining part in that alpha beta interval, the cosine of x negative. Then you need to take the negative sign. Okay? Then, after that, what's the form? You don't know, right? Nobody knows. Yeah. So under that situation, what can we do? Okay? Yeah? We may have that situation. Under that situation, this is our final form. Okay? Yeah. That's the final form. Yeah. We cannot remove our sine cosine. This is our final form. Okay? Yeah. So be careful in this situation. Yeah. What is the given interval? Okay? Yeah. Yeah. What is the given interval? Yeah. That's the complex part. Okay? Yeah. Yeah. For us, the simplest situation, yeah, we work on this problem, we work on a particular interval, AB, and we know on that interval, cosine function is non-negative or negative. Yeah, it's clear. There. Yeah, so we have one of the two versions, either the first one or the second one. Okay? Yeah. So then we can get this, final simplified version. Yeah. Yeah. This, because at the end, we can write this. Yeah. Because this C star part plus minus C star part, we can use 1C to represent it, right? Yeah. So here, although you see two different signs here for the C star constant, yeah, can we replace these two forms by one general C constant? Because this little c constant is arbitrary, right? It could be positive, it could be negative. So this little c constant covers both cases. Yeah. Okay? Yeah. So here we just use the style in our textbook. Because in our textbook, in this situation, because this situation we want to use a temporary constant. So we use this C star. Yeah. That's the temporary constant. Okay, the final constant. This is the final constant. Yeah. So final constant, we remove that star. Okay. So that's our textbook style. Yeah. But when you have this final formula, simple, yeah, pretty simple, right? Pretty simple. You need to understand we have some simple condition behind it. Yeah. Some interval. On this interval, we have one of the two cases on this interval. Otherwise, yeah, if on this interval, part of it cosine of x non-negative, part of it cosine of x negative, then we cannot get this one of the two forms. We have to take this relatively complicated form. We keep that form. Okay? Yeah. All right. Now, so we can continue. We need to determine this little c constant by the initial condition plug in. Yeah. So we can find the little c value. Yeah. And at the end, we find the final solution. Yeah. So the final solution, yeah, let me erase this place. Final solution. Yeah. Okay, yeah. Some little things. Okay, some little things. Yeah. So here, let me still keep that AB. Yeah, otherwise, you may. Yeah. Okay. Yeah. Some certain appropriate interval. Yeah. 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 So that's the one example. Yeah. Yeah. So in your calculation, you need to be aware of it. Okay. Yeah. You need to be aware of it. Yeah. Yeah. All right. Okay. All right. Problem 10. Application problem. Hormone level. Yeah. So let's look at the question first. Assume that the level of a certain hormone in the blood of a patient varies with time. Okay? Yeah. Now we need to calculate level of hormone, yeah, as a function of time t. Yeah. All right. Suppose that the time rate of change derivative, okay, derivative of this hormone level, yeah, is the difference between the sinusoidal input, yeah, yeah, sine function, sinusoidal, yeah, that wave shape, sine, yeah, function, yeah, input of a 24-hour period from the thyroid gland and a continuous removal rate proportional, yeah, let's understand this long sentence, to the level present. Yeah. All right. So here, the equality. So this long sentence gives us the equality. What's the equality? Y prime. Yeah. If we use the Y function, rate of change of this level of hormone Y function Y prime equals the difference. Okay? Yeah. Two terms. The first term, the input, and the input function is given. Okay? Yeah. Sinusoidal. Yeah. So based on this word, you can use the function shape should be the same as the sine function, the shape sine function, but location could change. Yeah. So this sinusoidal input gives you the information, just the shape of the function is the sine function. But what is the location of the there is a location factor, right? Yeah? The location factor is unknown here. Okay? Location factor is unknown. Yeah. All right, I will write down your name. Yeah. At the break time. Yeah. All right. All right. So that's the first term. And there is a second term. Difference. So minus the second term. The second term, yeah. Okay, second term, yeah. So 24-hour period, so that's associated with the, that sine function or cosine function. Yeah. Continuous removal, okay. Removal rate. What's the removal rate? Okay, minus certain removal rate. But the removal rate is given in another relationship. What's that? The removal rate is proportional to the present level of hormone, Y function. Yep. Y function, okay? Proportional, there is a constant multiple of Y function. That's the removal rate. Okay? Yeah. So that's the interpretation of this relationship. Yeah. So we can set up one differential equation, ODE. Set up a model for the hormone level in the blood and find its general solution. Find the particular solution. Yeah, here. Yeah. So this particular solution satisfying a suitable initial condition. All right. Yeah. Okay. So let's work on this question. Modeling. Yeah. So Y function, the hormone level at time t. Yeah. Interpretation of the relationship. Yeah. Yeah. Equality. Yeah. So first, we need to understand this sinusoidal input. Yeah. Shape of sine. Yeah. But there are two factors we need to control the shape. One is location. Okay. Yeah. Another, the frequency, because the sine function has a frequency, right? Yeah. There is a frequency concept when you draw sine function. Yeah. Sometimes the frequency is higher. Yeah. Let me show you the shape of sine function. Sometimes the frequency should be relatively higher like this. Okay. Sometimes the frequency lower like this. Okay. High frequency, low frequency. Right? Yeah. So which one? What is the real frequency you want to use here? Unknown. You need to determine it. Okay? So two factors, frequency factor and a location factor. Okay? Yeah. So we need to use certain parameters because we do not know that information at this point. So here we can see we need to use a few unknown parameters. Later we need to determine it. Capital A, capital B. Okay? Yeah. Two parameters. Yeah. Omega, little omega inside. Yeah. Here we use the cosine function. Cosine, sine, the same shape, right? Yeah. So you can use sine function. If you like, you can use sine function. So you can use sine function or cosine function. But the difference is the AB could be different. AB could be different. So you need to adjust the location. Yeah. You use AB. A, yeah, so horizontal location. Okay. B, the magnitude. Okay. Yeah, because your sine function, how large is the magnitude? Right? Yeah. Yeah. So you need to adjust. Yeah. All right. Then omega. You adjust for frequency, right? Yeah? Omega, larger, smaller. Yeah, you can change the frequency. Yeah? So that's our understanding of this input. All right. Here, the relationship between sine and the cosine. The angle difference, pi over 2 difference. Okay? Yeah? So we don't worry about using sine or cosine. Either one is fine. But you just change the angle. Okay? Yeah. All right. Then, now we need to figure out little omega. Okay? We need to figure out little omega. Based on the information, 24-hour period. 24-hour period, what's that? That's not frequency. Period, related to frequency. Yeah, closely related to frequency, period. Okay? Yeah. Reciprocal relationship. Yeah. So the period thing, yeah. All right, let's look at the period of cosine function without omega. Okay? Sine function without omega. Is that period 2 pi? Yeah, 2 pi. Without omega, 2 pi. Now we need, after we add omega, multiply omega on this variable. Yeah. Theta is the variable. Here, t has the same role as theta, variable. Okay? T variable, theta variable. Yeah. So now let's work on omega theta plus 2 pi. Is it the same as when you add 2 pi on cosine function? Do you get the same value? Same function value, right? Yeah? Yeah. So when you treat omega times t as one whole angle, you add 2 pi, you do not change the value, right? All right. So let's write, because omega is a constant, we can factor constant out. After we factor little omega out, inside the parenthesis, then the variable part, okay? Variable t plus 2 pi over omega. That's the variable part, okay? That means after we add, this is a constant, right? After we add this constant to our variable, then we apply cosine or sine, the function does not change, okay? Yeah. Can we treat this constant as the period of this function? Yeah. With this omega here, yeah. With the omega here, now the new period is this. This is the new period. Okay? Yeah. What's the definition of period? Okay? You add a constant on your variable, t, and your function value does not change. That's the definition of period, okay? So we add this constant on this variable t directly, yeah, then multiply omega outside, yeah, then we apply cosine or sine function, the function value does not change. So that's the period of definition of the period. Okay? All right, yeah. So this is the new period. New period is given, it's 24 hours. Period is given, 24 hours. Number given. Okay? All right, yeah. So we can solve this simple equation for omega. 2 pi over omega equals 24. Time unit hour. Okay? Yeah. So omega should be pi over 12. Okay? Yeah. The unit, you know, 1 over hour. Okay? Reciprocal of hour. Yeah. Okay. So omega, you determine omega. Okay? So next, capital A, capital B. Right? Yeah. Capital A, capital B, yeah, because here, find particular solution satisfying a suitable initial condition. So that could be determined by suitable initial condition, right? Yeah, otherwise, how do we know capital A, capital B? Right? Yeah. All right. Removal rate given. Yeah, removal rate proportional to the level present. That's y function. level present this function, right? Yeah. So capital K constant times y function. Yeah. All right. Yeah. Now we can write the ODE. Yeah. We call the mixing problem. Yeah. So this model, it's different from our mixing problem. Yeah. But you can see the rule. Okay. Yeah. Yeah. Because inflow outflow mixing problem, right? Yeah. Inflow outflow. Yeah. So from that behavior, there is some similarity with this mixing problem. Okay? Inflow, outflow, right? Yeah? Yeah. Inflow, input, outflow, removal rate. Outflow, yeah? From that point of view, similar. Yeah. So there is some balance law related to it. Yeah? So y prime, yeah. Yeah. So the balance law, that's for the mixing problem, salt inflow rate minus salt outflow rate. Okay? So here we just change the content, right? Yeah. Hormone level. We use hormone level. Okay? Yeah, the pattern looks pretty much the same. Yeah. All right. All right. Then our final version of the ODE in this one. Yeah. This input part, yeah, two terms. The first two terms, input part, then the output part. Okay. Yeah. Okay? Yeah. All right. Next, yeah, we try to solve. Okay? All right. We try to solve, yeah, if we, yeah, because the question, original question gives us some freedom to choose appropriate. Yeah, yeah, because the question, set up, a certain initial condition, right? Yeah. So the question allows us to choose some constant. We just choose the simplest constant. How about that? Okay? Yeah. If the question gives us some specific condition, then we need to apply this given condition to determine the constant. Yeah, but now it gives the freedom to us. So we choose A, B, and K, the simplest one. Okay? All right. Then we need to solve this ODE. Okay? Yeah? First order linear non-homogeneous ODE. We have the formula, right? Yeah. We have the formula. Yeah. P function is 1. P function here is 1. So simple. R function, yeah, this is the R function. Okay? So we apply the formula to solve it. Okay? Yeah? Yeah. And we calculate the H, very simple H. Then we write the final version of the solution function y in this way, then do the calculation. Okay? Yeah. So this one I put it in further explanation. Yeah, because it's pretty straightforward. Okay? Yeah. 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 Most of you can do it easily. So I can save a few minutes here. Yeah. Yeah. All right? Yep. So that's our problem 10. Yeah. Next one, Bernoulli equation. Yeah. Bernoulli equation. And because population dynamics. Yeah. So we study some special ODEs. Special ODEs. Yeah, some, interesting topics. Yeah. All right. So let's look at it. Yeah. So we still have 10-something minutes before the break. So let's look at a few slides. Yeah. reduction to linear form Bernoulli equation. Yeah. So Bernoulli equation. Yeah. Let me give you the form. Okay. Yeah. So the form. Look at this place. There is a y to the a part. Yeah. That's the special place of this equation. Okay. A is a constant. A. Yeah. A can be any real number. Yeah. Any real number. Okay. Yeah. Here you can see Bernoulli equation is not a linear. ODE, not linear. Yeah. Because of this term. Okay. This term, y to the general A. Yeah. For the general A, nonlinear. But for special A, it could be linear, right? Yeah, special A. For example, A equals 0, it's linear. A equals 1, also linear. Okay, yeah. But for other A, yeah, not linear. All right. But there is a little trick to convert Bernoulli equation to a linear equation. There is a small technique. Yeah. All right. Yeah. Cases of Bernoulli equation where A is 0, yeah, so it is a non-homogeneous linear form. This form, and we know how to solve it. Yeah. We have the formula. Yeah. All right. Then A equals 1, it is a homogeneous linear form, yeah, because we can combine the y term, yeah, left-hand side, right-hand side, yeah. Then right-hand side, 0, homogeneous. Yeah. So we know how to solve it. Yeah. Because it's separable, right? Yeah, separable. Okay. ODE. Yeah. So these two cases, the simplest cases. Yeah. All right. Then, for the general case, the non-linear form case, yeah, then the special technique, substitution in special form. Yeah. So we use a special substitution. Yeah. We can, get rid of this annoying term. Yeah. What kind of substitution? Let u function be y function to the 1 minus a. How do you know it? Yeah. So Bernoulli found it. Yeah. 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 First, this equation comes from some real-world physical problem. Yeah. So Bernoulli studied that physical problem. Then, yeah. So the equation follows this form. Then how to solve? Yeah. So try many different methods, try very hard, yeah. And finally, one day, suddenly, yeah, discover this special substitution. Then it works. Yeah, yeah, yeah. So that's the, typical, research. Yeah. All right. Derivative by chain rule. Yeah. So then let's take u prime derivative by chain rule. U prime equals that. Okay. Then we write y prime. Yeah. Y prime in this form. Then, so let's go back to the original equation after cancellation. Yeah, because we can do some division, right? After division by this function. Okay. After division by that function, we have this form, but this part is u, right? Yeah. So you can see the good thing is this part corresponds to u. Okay? Yeah. So then we get a ODE about u function, and this is a linear, first order linear ODE, right? Yeah. With special P function and R function. And we know how to solve it. We know how to solve it. Yeah. After we solve it, then we go back, we can find the y function. Okay? Yeah. Yeah. So for all constant a, little a, yeah. So we have the solution. We have the, explicit solution. Yeah. Yeah. So that's the, Bernoulli equation. Yeah. Yeah. All right. Then, yeah, we still have a few minutes. Yeah. So let's do another slide. Logistic equation, it's a special case of Bernoulli equation. Yeah. So there are a few special ODE. Yeah. So following the Bernoulli equation format, yeah, useful in the real world applications. Yeah. So one is this logistic equation. What's that? Y prime equals constant capital A y minus capital B y squared. Yeah. So that's the one special case of Bernoulli equation, but logistic equation. Okay? Yeah. So there is some physical background. Yeah. All right. Yeah. So these two constants not equal to 0. Otherwise, we have the simpler ODE we saw before. Yeah. All right. Solution. Yeah. So we use the substitution in the previous slide. So y equals y to the negative first. Yeah. Reciprocal of y function. Yeah. If you do that substitution, you can simplify the original equation to this new simpler equation. U prime plus AU equals B. Yeah. That very simple first order linear ODE. And we have the formula. Okay? Yeah. The solution formula, yeah. We can find it easily. Yeah. All right. Yeah. So this formula we can calculate the solution easily. Yeah. H, yeah, because P is capital A. Okay. So H equals AT. Yeah. Then U, so we plug in, yeah. And the result is pretty easy. Yeah. Then we need to write the final. Yeah, because you need to go back to y, right? So final y formula, reciprocal of this. Yeah. All right. Then we need to have some discussion on it. We need to have some discussion on it. Okay. All right. So another way to write it, yeah, equivalent way, yeah, but we just multiply numerator denominator by capital A, so we get this form. Yeah. But here, when we use this we can treat as the standard method. Standard method solving Bernoulli equation. Yeah. So you get the final formula. But when you do in this way, yeah. Did you miss something here? Did you miss some little thing? Not big. A little, something very little. Think about that. In one of the steps, you may miss something. Yeah. And that little thing may cause some difference. Yeah, let me point it out. Yeah, point it out. look at our variable substitution step. This is, in this step, you let u be reciprocal of y. When you do this substitution, do you miss something? Is there some special case you ignored?
What, 0?
Yes. Because when you make this substitution, you assume y cannot be 0, right? Yep. If y equals 0, how can you use that substitution? You may not be aware of it, but you skip that. You skip one little case, y equals 0 case. You skip that. Next question is it possible y equals 0 is also a solution? Is it possible? Y equals 0. If you look at the original equation, is y 0 also a solution? Yes. Yeah. Yes. So you need to bring it back. Because your substitution skipped this solution. Yeah. So at the end, you need to be very carefully check that missing case. Okay? Yeah. So you missed that. That's what. So you need to add it back. Y equals constant 0. Here, y equals 0, it means y is 0 constant. Y is a 0 constant. Okay? That's a solution. That is so we call it trivial solution. Yes, it is a solution, but it's a trivial. Okay? Yeah, trivial solution. Yeah. Then, this solution is non-trivial. Okay? This is solution non-trivial, right? Yeah. So y equals 0. We call it trivial solution. But there is a non-trivial solution. Okay? Yeah. This non-trivial solution, the y function value can never be 0, right? Can y take 0 sometimes? Is it possible y of t at certain t, it could be 0? No. Okay? Yeah, because a is non-zero. Okay? A is non-zero. Non-zero constant at the numerator divided by something at denominator. It cannot be 0, right? Yeah. But is it possible denominator could be 0?
Oh, I guess C is...
Right. At a certain t. At a certain, yeah, because your t is a variable. Okay? C is a fixed constant. Yeah. Is it possible, yeah, after C is determined, yeah, in the real world application, C, A, B, C must be given. Yeah. In that situation, is it possible for certain t, so this denominator becomes 0?
Yeah, I thought you were asking if the whole bottom denominator could be 0.
Yeah, the bottom. Yeah, the bottom. The
C and B
right. Yeah, the whole denominator could be 0, right? Yeah. It's possible. Yeah, but if that happens, imagine that graph. Okay. Yeah. At point t, yeah, because 0, infinity, right? Yeah, infinity. There is a peak. Okay. The graph, there is a peak at certain t value. Yeah, infinity peak. Okay. Yeah. Things like that. Yeah. Okay. All right, let's take a break. Then I'll come back at 7:15. Yeah, 7:15. We do the second half.